Crappity-doo-dah. All right, you guys missed everything. So if I do 9 minus 6.5, that's how far apart 9 is from the mean. If I divide that by how big each standard deviation, I often call standard deviation steps, right? Because if my data is really wide, spread out, how do I move around in it? Big-ass steps to move around in it, right? If my data was really tiny and I used big-ass steps, I'd miss the data entirely, right? You guys kind of with me? So standard deviation tells me how big my tick marks are, how big my steps have to be to get around in the data. So I want to know relative to how big each step is, how far apart are those two? So 9 minus 6.5 divided by the standard deviation, which is 2.236. What do you get for that? 1.118. So it's just a little bit more than one step up from the mean. If it was negative, it would be a little bit one step down from the mean. So negative output just means it's below. Positive means it's above. You guys kind of with me? So the reason it's in section 3.4 is it's a measure of relative position. So you can take your quiz score minus the average quiz score divided by the standard deviation of the quiz scores and see relatively where you were. So if you made a 40 on a test, but the average was a 38, then relatively you're better than average. Your score from this would be positive something, right? You kind of with me? Okay, good. So it's better than absolute scores. It's relative to what happened. Right? Yeah, maybe. So this last thing is actually kind of huge. Because a huge part of statistics is all about figuring out where things fall for the most part. So if you're going to go to college, has anybody ever heard of the Princeton College Guide? It's for you guys. If you look up some colleges, they always show you the middle 50% SAT scores, for example. So you're always curious about where's the big chunk of students falling in the SAT scores or GPAs. Right, so that's kind of like what this is talking about. If I go one step out from the mean, how much data do you catch? And you can imagine, if I go several steps out from the mean, I should catch almost all the data. Because if I pull my data farther apart, what happens to my steps? They get bigger. So it's like the data can't escape, right? If they start getting further away from me, my steps get huge, and I can catch up to them, right? So if I only go one step out, what was the mean? Again, part C, I don't know what I said. The mean is 6.5. If I go one step up, so I add 2.236, I get 8.736. And if I go down, 4.264, cool. Now, for some reason, this is another place where students freak out a little bit, but just absolutely do what it says. How many data points fall between those two? Does 4 fall in here? No. Of course not, because it's over there. So 5 does. So how many 5s do we have? So there's 2 5s. So let me see. How can I do this quicker? So you guys should have this. This is why it was easier to sort this for later. So 5 falls in there. 1, 2. 6 falls in there. 3, 4, 5, 7 falls in there, right? 6, 7, and that's it. 9 does not fall in there. It's above the 8.7. You guys semi with me. So what falls in here is 5, 6, 7, 8, and that's a total of 7 data points. Out of how many total data points? 12. So a little bit more than half fell in there. How much exactly? 58.3 PM. Yes, cool. So a little more than half fell in there. How are we doing? Now think about it. You would expect, if I go to the mean and I go one step up and one step down, unless I have a really freaky distribution, I would expect to catch some stuff. And for most data sets, I would expect to catch a decent amount of stuff. You kind of with me? If I took 2 steps out, now it's almost impossible for something to get away. All right, how are we doing there? Because I immediately want to segue from that to some theory. This is hard, nice, concrete. You can see it, you can count it, you can look at it, you can crunch it up, right? So let's talk about theory for a second. Can't get away from theory. Especially not with me. All right. Focus. So here's the theory. And this is still section 3.3. This is in 3.3. First part of the theory we have is Chevy Dude. Well, Chevy Chev is his name. I'll call him Chevy Dude. I don't know why. I have no idea what it looks like. Chevy Chev's theorem. And this comes from what I was just saying earlier. I'm going to use a certain made-up distribution. I'm going to use it several times this semester, just because it's a really good visual. If I went to Florida and I took everybody's age, here's one way it could possibly break down. So this is Florida in a parallel universe. I could have a bunch of young people, so it would look like that, right? And I could have a bunch of older people. You with me? And then I could have nobody in the middle. Right, so I could have some newborns up to like 25 years old, and then starting over at 40 years old up to 90 or whatever. Right? So forgive my scale, but that's all right. How are we doing so far? So the mean of this would be somewhere in there, right? Okay. So it's possible. Now here's what Chevy Chev said. He said a few things. He actually said one thing. We're going to break it up. He said, within one standard deviation of the mean. And what the hell does that mean, what I just said? It means if I go up a standard deviation and down a standard deviation. It's possible that I could catch at least 0% of the data. Which if you think about it is like, wow, way to go out on a limb, dude. Right? But you got to give him a break. Everything he says deals with any freaking distribution you could imagine. Any list of numbers you could possibly make will do everything he says. The first thing he says is very lame. I will give you that. But he does say it could be empty. So that's kind of huge, right? Go one step out, it could be empty. Within one standard deviation of the mean, why did I write the word at? Within one standard deviation of the mean, there is at least, oh I see, that's why. 0% of the data. So far he's right. We got 58.3. That's at least 0%. Yay, Chevy Chev. Now here's the second thing he says. Within 2 steps of the mean. So if I take another step out, within 2 standard deviations of the mean. What's up? Can you read?
Another time. The first.
So within 1 standard deviation of the mean, there is at least 0% of the data. Within 2 standard deviations of the mean, there is at least 75% of the data. I really want you to understand. Just make up any list of numbers you want. If you go 2 steps out like we did on that sheet, just go 1 more step out. Any list of data you can imagine, you will catch at least 3/4 of the data you made up. I don't care what kind of numbers you put down. That's kind of really freaking huge. Makes up for the first statement a lot. Right? And then the third thing he says is within 3 standard deviations of the mean, 89% of the data. Okay. Now, I'll tell you this. You don't have to memorize these numbers. They will show up in the homework. You will have to memorize the next rule we're going to look at. You will have to know this one. This is a nice idea. And again, why does it make sense? I mean, I could try to escape. If I was God, I could reach down and say, you become younger, you become older. And of course, why won't that work? Why won't I escape? Like I said earlier, what's going to happen? Yes, standard deviation gets bigger. So if I do grab these people and make them young, so these people are not even born yet, too bad for you guys, and I make these guys older, oh shit. My standard deviation, my step gets bigger now. So I still catch the same amount at least, right? Now, there's no way in hell we're going to go into the math behind why is it that. Trust me, you don't want to see that. It's another class entirely. But we are going to stand on his shoulders and say, thanks, Chevy Chev, for that work. Sweet. So real quick, if I went 1 more step out, Let's see if Chevy is right. If I went one more step down, where do I end up? If I do minus 2.236 again, I end up at 0.028, I think. 0. 2. What am I doing? And if I add one more step up, I end up at 10.9. Let's see if we can do this one, Jeff. Yay, maybe. You guys with me? So I took one more step down, one more step up. And what data points do I catch now?
All of them.
All of them. So I get what percent?
100.
All right, so it's still right. So at least 75%. This is a very basic set of data, right? There wasn't anything weird about it. It was kind of like all over the place. So you can try to do weird stuff to it, make a bunch of 1s and a bunch of 9s or whatever, and your standard deviation grows a bit and catches stuff still. It's still going to follow this process, this rule, this theorem. Okay, maybe. All right. So if I ask you, if I said there's a distribution with a mean of 10 and a standard deviation of 1.2, between what two data points will you find 89% of the data at least? This is easier than you think. You do like we did on that paper. You draw a little line, you put the mean in the middle. How far out do you have to go to catch 89%? 3 steps, right? 1 step is nothing, at least nothing. 2 steps is at least 3/4, and 3 steps is at least 8/9. Or 89%, same. So if I have the mean in the middle, 10, what's 3 steps up? Yeah, 3 steps would be 3.6. So 13.6, right? 3 steps down would be 10 minus 3.6. Who is it?
6.4.
Yeah, 6.4. Like, I don't know why I was. And then, so that's the answer. Between 6.4 and 13.6, I'm guaranteed that there's at least 89% of the data. Right? You guys kind of with me? What's really powerful about this is that this works, I don't care what the distribution looks like. It just works. So I know, if I, remember, what was the, let me give you some real life stuff. Remember the mean quiz grade? Oh yeah. The mean quiz grade was a 78.4, and the standard deviation was 13 point, we'll just make it 13. So between what two data points would I find 3/4 of at least of the quiz grades? You would go here, go up 2 steps, right? So you take 78.4 and you add 26 to it. Well, that's kind of, 104. Yeah. And you subtract 26 from it, roughly. So I'd expect to find at least 3/4 of the grades between those 2 data points. You with me? Okay, maybe. Now let's move on to something that's more powerful because it only works with a certain kind of distribution. And probably the distribution that we talk about every now and again. What's the most important distribution? The more you say that, the more drunk you sound. The distribution. What's the most important distribution there is in statistics? Normal. And actually, it's not exactly true what I just said, but for us, that's the most important distribution. And what is it, if I know it's normally distributed, the thing I just had up here could never happen, right? What's it got to look like? It's got to look like a bell, so it's got to start low, go high, come back low, right? So obviously, within, now I sound even more drunk. Obviously, let me drink this tea. Oh yeah, okay. Obviously, within 1 standard deviation, let me use total symbols here just to really get us going. So this would be mu minus 1 standard deviation. This would be mu plus 1 standard deviation. Oh, yeah. And to make this better, well, screw it. We'll do this a little bit later. Too bad. So within 1 standard deviation, it obviously can't, I can say more than just at least 0%. I mean, that's blatantly obvious here. I want to be much more precise. And to tell you honestly, since its normal distribution is so rigidly defined, I know exactly, I say exactly, this is even a little approximation, there's 68.28 or whatever the hell it is, but 68%. So if I know something's normally distributed, like men's heights are normally distributed, if I took the average man's height, added one step, subtracted one step, that 68% of all men in the U.S., right, would be between those two heights. You guys kind of with me? Mm-hmm. So I can use that information to figure out how tall to make doors, right? If I want a certain percentage of men to have to duck, I don't want it to be very high a percentage, I don't want to get a lot of complaints, I can just figure out, well, how tall do I have to make it so that a certain percentage actually fits through without ducking. Are you guys kind of with me? Or airplane widths. I'm sure you heard the thing about all the airplanes had to increase the seat size to fit us, right? So they took the average hip width, which is increased, and the standard deviation, and they figured out they only want to get so many complaints, so they made it so that only a certain percentage wouldn't fit in a seat. Are you kind of with me? This is the immediate applicability of statistics. You're basically there. You can do a lot of shit in the real world with the little bit that we know at the moment, right? Very dangerous. So the 68%. If I go one more step out, and mu minus 2 steps and mu plus 2 steps, this is going to be 95%. So there's only 5% outside of there, right? Only 5% down here, only 5% up there. So for example, real quick, a concrete example before we get too far. Men's heights are normally distributed with a mean of about 69, and a standard deviation, I think it's 2.8. We'll just go with that. So what's one step up and one step down? Yeah, 71.8. 66.2. Right? And then so there would be 68% of all men would be between these two heights, 5'6" and almost 6 foot. Right? 68% of all American men are between those two heights. That is a powerful statement to be able to make. If you think about it, you could do a lot with that information, right? Now if I go one more step out real quick, just bear with me here. 63.4. And this would be 74.6. So what percentage of men are here? Yeah, what'd you say? 2.5%, because in here there's 95%. There's 95% between those, right? So outside of there is 5%. So there's 5% less than this, and 2.5% less than that, and 2.5% more than that. So if I made my door this tall, 2.5% of men would have to duck or miss the duck opportunity and knock themselves out, right? You kind of with me? So that door, I think we measured that one here, and it was like 77 inches tall. So they really kind of, why not, right? Everybody, don't duck. No limbo. You get in. Now, last thing it says, if I go one more step out, and thank God this is the last step we'll take, right? One more step out, I actually catch 99.7% of the data. So if you have a normal distributed data point, right, like men's heights, women's heights, SAT scores, if you know the mean and you go 3 steps out, you've basically caught everybody. You've only left out 0.3% of the people, which is not a lot, right? You guys kind of with, okay, cool. Okay, so this is called I gave you this whole thing, didn't tell me what it's called. It's called the Empirical Rule. And it's called it because empirical actually means based off of observations. When you hear that word empirical, so most science courses are empirical in nature because you do something, you see what happens, and then you remember that. And you go, that blew up, so I'm not going to do that again, right? So this is less theory and more computer simulations that actually went through this. It's done by observation. So it's kind of neat. And then you can back it up with theory. Oh, let's see where I want to go from there. Oh. So what I want to do is I want to tie together what we said earlier. That little x minus x bar thing we did on the handout. So if I had a normal distribution, or actually really any distribution, but let's just say it's normal. And let's say the mean is 20. And let's say the standard deviation is 12. Then how far away, how many standard deviations away is 32? I'll start easy. How many steps does it take to go from 20 to 32 if each step is 12 big? One step, right? If I start at 20 and every step I take is 12 inches, I'll get to 32 inches, right? So this will be one step. So how far away is, how many standard deviation away is 34.78? 2. I want to know, 2 would be 2 12s, right? You with me? 1 12 to 32, another step would be another 12 to 44. So it's not that. It's going to be a little bit more than 1, right? How would you find out exactly how many steps fit in there? You do exactly what we did earlier. You take the data point you're interested in. How far is that away from the mean? This far away, right? And then to see how many of something fits into something, you divide it by that, don't you? How far you got to go, divided by how big each step is, will tell you how many steps fit in there. So x minus x bar divided by s, which here is 12. So what do you get if you do that? 1.232. Okay, cool. How are we doing so far? We call this thing, you know we got to give this thing a name because it's stupid important. We call this thing the z-score. So standard deviation is what I measure things in statistics, sort of like in inches, centimeters. So standard deviation is my inches and centimeters. Z-score is how many inches or centimeters something is away from the mean. So standard deviation is setting up my tick marks. Z-score is laying the ruler down and actually making a measurement. You guys, I love that analogy. I always wish that my statistics teacher would have just said the damn thing, because that's exactly what it is. Okay. Maybe.
So, standard deviation is a measurement in statistics.
Z-score is a measurement. Standard deviation is the unit I use. Do you see the difference? So if I say you're 16 inches away from me, 16 was a measurement I took. Inches is the units I used. Right? So that would be, inches would be the standard deviation. And the actual measurement I took would be the z-score. So what's the units on this? Standard deviations. So this tells me the number of standard deviations from the mean to the data point. That's what a z-score tells me. Let me say that again, because let me say this, and then suddenly you guys are going to be very interested in me repeating that definition, because every single test I will ask the same question, and someday I'll have less than 10 people get it wrong. All right. I'm giving you exactly, this is exactly on the test. This is, I'm going to say, tell me what a z-score tells you in general. What does a z-score tell you in general? Ready? Ready. Z-score tells me the number of standard deviations from the data point to the mean. So there's a lot of different variations on that, right? Say how far from the data point to the mean, measured in standard deviations, all that kind of crap, right? So z-score tells you, I forgot how I said it earlier, the number of standard deviations from the data point to the mean. And if it's negative, it just means it's below. So if you had a negative z-score on your quiz, you were below the average. Positive z-score, above the average. What if you're exactly average? What's your z-score? 0. I love it, because it's 0 away from itself. Kick ass. So a better way to represent this is 0, 1, -1, so forth. You see? I don't need all this writing that I did if I just talk about it in terms of z-scores, the number of standard deviations away. Okay, maybe. You don't understand how important this is, what we're doing right now, because chapter 6 and beyond is going to be built off of everything I just said, basically. Everything's going to depend on that. Okay. Yes, sir?
So is Z-score, are those the steps?
Z-score is the number of steps.
Okay.
From something to so how far apart are these? That doesn't even make sense until I talk about, well, what unit of measure are you going to use, right?
Oh.
So the standard deviation is the unit of measure I use. So how far apart are these? 1.23 standard deviations apart.
Is that how you want us to write it on the test? Is that 1.23?
Depends. If I ask you what would a z-score of 1.23 mean, you would say it means that data point is 1.23 standard deviations above the mean.
Okay.
Cool. So it kind of depends on how I ask.
Okay.
If I just say calculate the z-score, you don't have to say 1.23 standard deviations. You just say 1.23, right? Okay, good. Okay. I got to stay there. All right, let's take all this away. So, if somebody got 71 on a test, but the mean was 78, and the standard deviation was 11.2, what would their z-score be? So x always represents a single data value that you're currently interested in. U is the mean, standard deviation is sigma. So this is, I'm talking about, these are population, these are parameters, right? Because I'm using Greek symbols. Okay, good. So the standard, so see how the z-score formula is always the same? I know earlier we were doing this. Why were we doing this earlier? Because it was a sample. But I always have x minus the mean divided by the standard deviation. The z-score formula actually never changes. You're not going to believe me later, because it's going to change, it looks like, but it never changes. Never. So what do you get here? Yeah, so you get negative 7 divided by 11.2 is negative who?
0.625.
Coolness. And I'll tell you this, later we're going to use a table where we can only use z-scores out to 2 decimal places. So I might round z-scores to 2, and that's why. Later we'll use a table that you can only use 2 decimal places. So this tells me that this person made below the average, right? So what if somebody else is all like, nah, I made an 80, you suck. In another class. So this is one class. Like, I made an 80 on my test, you suck. But the mean here was a 88, and the standard deviation here was a 5, what do you want to say, Jeff? 5.13. So the z-score here would be the data point minus the mean divided by the standard deviation. And what do you get?
Negative 1.55.
So who did relatively better? The first dude did relatively better. You got it with me? It's probably not going to do much to argue with this guy. We need 80, you made a 70, what the hell are you talking about? Your stats. Get away from your stats. Right? So maybe. So this is what I mean by it's a measure of relative standing. It's relative to what the data itself looks like. So it's not, absolute scores really don't mean anything. When you take the SAT, they don't give you an absolute score. They give you a relative score based on relative to everybody who took that test on that day. You don't get an absolute score. You guys kind of with me? In fact, we're going to talk about what the hell you get here in a minute. I got to hurry, guys. All right, let's see. I think that's mostly section 3.3. Yes, cool. Okay. So you just got to get in there and try some of these problems out. The Chev's theorem, the empirical rule. Got to try those guys out. Okay. All right. Let's do section 3.4. To be completely honest, the z-score is in section 3.4. Yeah, not too bad. But it's not all 3.4. 3.4's got some other stuff in there too. So, anybody taking the SAT at all? Do you remember what you get back? What is it they tell you? You don't have to tell me your score.
Suck.
They say you suck?
Yeah.
You're the you suck percentile.
They give you like a score out of something.
Yeah, I tell you honestly, I don't even know what they make it look like nowadays, but they should tell you you're in the 82nd percentile.
Oh, yeah.
Or something like that. That doesn't mean you made an 82. What does that mean? If you're on the 82nd percentile, which is way too many letters for me to write, so I'm going to call that P82. That's what the book does all. That's what we call it. And in general, P82 is the 82nd percentile. What the hell does that mean? Is it good? Yeah, it's better than the 28th percentile, right? Why? What does it really mean? Good. You scored higher than 82% of the other people that took that test that day. Right? So if everybody sucked, you could have a relatively low absolute score, but a high percentile. Does that make sense? Because if everybody sucked, but you're still here, and most people are there, you're great. And now you start to see that's related to curving grades, right? So if everybody sucks, I could just call a 20 a C, and suddenly everybody did okay, right? And that's grad school. That's basically what grad school is. It happens here too. All right. So let's talk more detailed about this. So this definitely means you did higher than 82%. Your score was higher than 82% of other people's scores. So let me give you a specific example. This is a small sample, so it's not. Doesn't extend beyond what I'm about to talk to you about it. So we'll see if you guys understand what I mean. Here's a small little sample. I'll put it in order because percentiles don't mean anything unless they're in order. Does that make sense? You wouldn't just put your score, I got a 3, I'm above. No, you got to put it in order for that to make sense. How many is it? 1, 2, 3, 4, 6, 7, 8. I wanted it to fit. Here we go, Jeff. No, screw it. I don't want to screw you. 9, 10. Okay. I make 10 because then it's easy. Percentages are easy. Does somebody have a guess as to what that would be from that list of data? Good. That represents the 70th percentile. Does somebody have a guess as to what exactly that would be? So I have a guess of 41. Why did you guess that? It's crazy because it's the 7th one. But if it's the 7th one, how much is below it? 1, 2, 3, 4, 5, 6. So what percent is below that? Shit. So what's another guess? That's not right.
45.
Another guess is 45. Still not right, but I like it. If you have 70% below you, how much should be above you? 30%. Well, how much is above 45? 20%. Shit. So doesn't this feel like if I have 4 numbers, where's the median? And what do you think another name for the median is? I like that. But in terms of these. 50th percentile. So why did we cut the 2 in the middle in half? Because then it has 50% below and 50% above. So I have to do the same kind of thing here. Does that make sense? Median is a specific kind of percentile. So the work I have to do for these kind of things, will kind of mimic that a bit. So where do you think the 70th percentile is? It must be right in the middle. So it's actually what? 43. I love it. So let me show you what the work would look like, because not all your lists are going to be 10 long, right? You might have a much larger list of data. I want to have an algebraic kind of way or a computational way. I won't say algebraic. Computational way to get there. So the computational way to get there is 2 steps. First step is, where the hell is the answer? And the second step is, go get the freaking answer, right? So to find the 70th percentile, it kind of makes sense. How deep into the list do I want to go? How deep into the list do I want to go to find the 70th percentile? I want to go how far in? Do I want to go 50% of the way in? I want to go 70% of the way in. So the first step is I want to go 70% of the way in, and how big is the list? In this case, it's 10. So if I go 70% of 10, I'm at least getting close. Somebody from earlier say, but I was wrong. I know. So we got to do something to that, right? I don't mean you sound like that, by the way. 70% of 10. What's 70% of 10? 7. Now, here we go. Ready? If you get a whole number from step 1, you average that one with the next one. So I got 7. So the answer is going to be the average of the 7th and the 8th. If I would have gotten anything else, I would have rounded up. So if I would have gotten 7.03, I would have rounded up to 8. The answer would have been the 8th number. That's the only two things that can happen. So if you do this process, and on the first step you get a whole number, you average that with the next one. So this will be the average 7th and 8th. So the second step would be 41 plus 45 divided by 2 is 43 that we got. So, yes ma'am?
You said if it's 7.03, you get the 8th. So it's still 7th, 8th, or 8th and 9th?
No. If it's 7.03, the answer would be the 8th number, period. So you only have to average something if you come out to a whole number there. So from this list, what would P25 be? What's the first step? 25% of 10. What's 25% of 10? Since I got not a whole number, I round up and I take that number, right? If I round up, the third number is the answer. The second step is go get the answer. And the reason I make a big deal of that is I always have somebody tell me the answer is 7. No, you got to go get the answer, right? Somebody here tell me the answer is 2.5. No, you got to go get the answer now, right? Go get the third number. The third number is 19. So P25 would be 19. Now again, it's a very small sample, so it's not perfect, right? You could argue that 19 does not have 25% below it, has 20% below it, but there's only 10 numbers up there, so it's not going to be perfect. But at least got things started, right, for us. That's the general process for running any percentile. What do you think I could call P25 otherwise? What's another name for P25? 25% of the way through a football game means that's the end of the first quarter. So I can now call this Q1. Another name for this is Q1. So P50 is also known as Q2, which is also known as X tilde, right, the median. You with me? We said that earlier. The 50th percentile is the median because that's the thing in the middle. Okay, maybe. It all comes back together. Okay, cool. I'm tired of using that same board. Okay. So let's do something with this. Let's see. Let's make a larger set of data here. Bear with me. Alright, so 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Sure. Okay. Alright, just make a little bit bigger thing, not based on 10, so we can get away from that. We're going to find what's called the 5-number summary. It's kind of like we naturally want to break things into quarters. We do that with sports. We do that with a lot of it. We do that with money, right? So the 5-number summary would be the lowest number, Q1, Q2, Q3, the highest number. That's the 5-number summary. All right? You guys kind of with me? I can see some of you guys are definitely losing interest. I'm playing you too much. But we just got to get through this. Right? And this is what you see a lot of Well, let me get there. Because we're going to make a visual out of this, and it's what's called the good old box and whisker plot. Right? How's that for a freaky sounding thing? So the low and the high are easy enough. The lowest is 7, the highest is 61. We'll take care of that. How do I find Q1? Good. So I go 25% of the way in. So it's a fourth. And how big is the list? 16. So I want to take 25% is 16. 1/4 of 16 is 4. I got 4, so what does that mean? Average the fourth and fifth number. So I want to average fourth and fifth. So 1, 2, 3, 4, 5. So I want to average 11 and 14. And I get 12 and a half. Cool. So Q1 is 12.5. How you guys doing? This is the kind of work you got to show me. Because I am going to show you, the calculator just spits this out at you. I'm going to show you that here in a minute. But it's never good enough just to take that spit and put it on the paper, right? Okay. I don't know if you guys caught that. I said the calculator spitter. Q2. How do I find Q2? So half of 16 is... So I take the average of the 8th and 9th. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I want to average those. And of course that's 27 and a half. Is that cool? This should, please embrace this. This is not that hard, right? And then Q3, 75%. And here's the funny thing I wanted to show you. If Q1 says go 4 in and take that in the next one, Q3 is going to say 4 from the top. 1, 2, 3, 4. Average these two. Let's see if we get the same answer just doing it straight. What's 75% of 16? 3/4 of 16. 12. So I'll take the 12th and the 13th. And the 12th and 13th numbers, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13 there. I'd average those two, right? So if you, whatever number you get here, you do the same thing there from the other side because you want to go 25% in from the bottom. Does that make sense? Just trying to help you guys out a little bit. Or don't. Just count like I did. So Q3 is obviously 50. You guys with? All right, so that's the 5-number summary. Now let me show you how to make a box plot out of that. It's also called a box and whisker. All right. And then I'll show you how the calculator can give you all those values so that on a test you can double check yourself. Right? It's always nice to have a way to check yourself, like I didn't back in the day. All right, man. Okay, so this is let this be easy, please. Box plot is the book's evil thing it did to this interesting name of box and whisker. Oh, some of your faces. So what you do here is you make a scale that all of these will fit on. So maybe I want to start at 0 and go up to 65, maybe. So I can go by 5s or 10s. So I got 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65. Okay. So whenever you make a scale, you just want to make sure that there's a home for every data point. If you can't read that, you can make it yourself. Now you just put a line over each of the 5-number summary numbers. So I'll put a line, where's 7? 7's about right there. Put a line there. And then I got 12 and a half is about right there. 27 and a half is about right there. 50 is exactly right there. And 61 is right there. How we doing? That's crazy, right? Now you box off the middle 3. There's the box part of the box and whisker. How we doing? And then you whiskers out to the last pieces. Sure. Can somebody tell me what percentage of the data is in here, in this box? What was this again? Why did I draw a line there? What was that? What was it? Q1. So what percentage below Q1? What's the definition of P25? What percentage is below that? 25%. What percentage is below Q3? Bless you. 75. Q3. So there's 75% below that. So what percent is in between those two? 50. Just subtract. So that's the middle 50%. That's what I was saying earlier. It's always the middle 50% SATs, the middle 50% GPAs. The middle 50% is like, the heart of what's going on in your population. Or sample, whatever you're working with. You guys kind of with me? Because if this is a measure of radioactivity somewhere, I could then compare it to somewhere else. And where would you rather go? If you had to go to one of these two places, I would rather go here because there's lower radiation, right? Or you can talk about, comparing men's and women's grades on something and see if there's any big disparities between the two. So it's a very quick visual, and you can put one right on top of another population or sample and compare the two very easily. And in the homework, you're going to do exactly that in a couple problems. You're just going to compare the two and answer some questions about comparing the two. So let that be relatively easy. Let me show you real quick how to do this. We'll do it for that data there. Let's go back to the calculator. Go up here and clear this list out. Right? And then you can never have too much data entry in a class. Enter this data. Maybe not. Don't want to play along, just sit there and wait. Okay, cool. Thankfully, the last space is 17, which means we got all 16 data values in there, thank God. So now, you'll love this. Here's something you would have liked to have known earlier. Hit second quit to get the hell out of the list for a second. Right. Go to Stat, and I don't think we've gone here yet. Calc. And tell me, see if you guys can answer this question. I know we had trouble with this question before. How many variables are there? Beautiful. There's one variable. A lot of values for that variable, but there's one variable, and the made-up thing I just said, it was like radiation levels. That's one variable, right? So I want to do one variable statistics. So if I had two variables in list 1 and list 2, I could do two variable statistics, which we'll do later in the class. Not today, later in the semester. So do number 1, enter. And it defaults to list 1, so I got my stuff in list 1. I could just hit enter. If you had stuff in list 2, you have to tell it second to list 2. Are you with me? It doesn't know what you want, so it's going to default to list 1. Hit enter, and what do you see? First thing it tells you is the mean. Kick ass. Second thing it tells you is the sum of the x's, in case you want it. Then it tells me the sum of the squares of the x's, right? Which reminds me, I forgot to show you. Well, we got time. I love it. Aw, it's too bad. You can't get out of it early. What are these two things? Oh. Good. What's the difference there? And why does it give me both? Stupid calculator. Why does it give me both? It doesn't know. How would it know? We're the humans. We know if it's a population or a sample that we're putting in. So it says, I don't know, dude. Pick the one you need. Right? So this was a sample, basically. I said a sample of radiation. So I would use this if I needed the standard deviation, right? You guys with me? So be real careful about picking the right one. Tells me how many there are. Now see that little arrow? That means there's more stuff. So if you scroll down, what's that? 5-number summary. 7, 12 and a half, 27 and a half, 50, 61. Kick ass, right? Okay, maybe. So the last thing I want to show you, very quickly, I think I promised you this last time. So that's section 3.4. 3.4 is all about percentiles. It introduces z-scores and the box and whisker plot, which is just visualization of percentiles. The last thing I want to show you is, let me do the S. Real quick, and yes?
Can you fix the camera?
Oh, yes, thank you. I still need to get my TA hours so I can hire somebody. The more I say it, the more serious I become about it. Now, you could do an entire year of algebra of summation symbols. I'm not going to do that. I just want to show you the first couple steps so you kind of agree with the end result. I want to show you a different formula you could use. This is a little calculation intensive. See how this thing gave me sum of x and sum of x squared? And one reason that they do that is because I can actually use those two numbers to calculate the standard deviation directly. And I can just, bam! So after this first test, that would be a great place to go if I want you to use this formula, right? Just need to get those two things. If I could just rearrange this a little bit. Now, looking at that, what would you do in algebra if I said simplify that? Whoa. 4, thank you. All right, good. Because you can't distribute a square across the subtraction, right? Exponents don't play well with addition and subtraction because they're based on multiplication, right? So you got to FOIL this bad boy out. Oh, some of you guys are like, yes. So how do you FOIL this? You get x squared minus 2 of these, right? Plus x bar squared. You guys got it with me? Come on now, yes you are. This would be x minus x bar times x minus x bar, right? That's what squared means. And then FOIL, right? Right? Good. I had to take at least 103 again. All right. Okay, I told you there wasn't much algebra. I didn't say there was absolutely no algebra, did I? I said there wasn't much. So can you see how, this would come out of here? And see, x bar, remember x bar was the sum of x over n? Do you remember that? So I'm going to spare you some of this. I'm not going to go through the whole derivation of this. If you keep going with this and you bring this in, and here, oh my god, it'd be this squared and all that kind of shit, where you end up is here. Here's a whole other way to do the variance. Now, some of you guys will look at that and say, yeah, that's better, Jeff. But notice, what does this need? It needs to square the sum of x. I can see the sum of x. There it is. Plug a number in. This says the sum of the x squared. It's the sum of the x squared, right? It's just sitting there. Right? Or if I made you do this if you want to do this for the first test, you don't have to do this. You could just do this. Do you understand? Because if you make a list of the x's, add them up, bam. Make a list of the x squares, add them up, bam. Makes that even easier if you want to do it by hand. Now, if you don't want to touch this because you're throwing this in at the last minute, Jeff, what the hell? I don't blame you. But I promised you I would show you this because the book has this in a slightly messed up way. I showed you that at the end of class last time. They do weird shit and they do worry about the internal fraction in this. It's crap. This is a better way, believe it or not. So I'll leave it up to you to decide if you want to do this way or not. So you guys look really. So if you don't like this at all, you don't have to worry about it at all. There's the formula you can use right there. Yes, ma'am. Okay. All right. And that's. Oh, let me give you the practice test, and then you guys can go.
Oh my gosh. We're not turning this in, right?
Whichever way it's Taylor.
Yeah, and I there's a link that says the old homework for the old. I know. Once you figure that, put it up there in case. Yeah, you missed it. Okay, thank you. Yeah. So you have.
Yes. Hoping they don't forget it.
The list is just frequency list is something you take a whole other list which tells you like in list 1 you could have 1, but in the frequency list you could put a 7, which means you have 7 ones in your data. So it's just like you don't if you have 7 ones, don't put 1 1. Just put 1 7. Yeah. So, but you okay, yeah. Good, you're good. That's the extra thing. Oh.
Thank you.
Sorry. You need the same thing? Sorry, how did I miss you guys?
Was it very bad?
Somebody stole it.
Question. To get, would it be the fact that if we stop the cars one day and then 2 the other, and then the stop is 1.5? If you were to divide it?
Make it, yeah, it would be, you would have stopped 1.5 more times. But make it a little more obvious. If I stopped 6 today and 2 yesterday, I stopped 3 times as many today.
Okay.
So the division does make sense.
Yeah.
Even
I
though
was
1.5 makes sense, but it's just gross. But it's still
thinking-
1.5 times as much.
Okay.
Because what would a 0 mean?
No, nothing.
I didn't stop any, so 0 means what it's supposed to mean, and that's another thing of
Okay.
ratio.
Because
Good.
I got it now, because I was thinking more like the actual car itself.
Oh,
Not the actual
the number of cars.
Yeah.
Yes.
Yeah, okay.
But it is interval, but it's more. It's ratio too.
It's-
Subtraction
okay.
makes sense, but so does division. So,
Okay.
Yeah. Cool.
You did get my email. I put it back on my lab, but it was running super slow, like you said it was.
Yeah. Come to find out, I contacted the Pearson.
I was on hold for 30 minutes with
got
them. Some
issues
issues going on.
everywhere.
Oh, so it's not just.
They've got their guys.
Yeah, their IT guys all on that. Okay.
So yeah.
Didn't want to be just the only one.
Yeah.
Just let you know.
Oh yeah, yeah. So I haven't heard from anybody else.
Okay.
So I didn't want to put anything out there. People aren't having problems.
So it's just me right now. Yeah.
If you have trouble finishing it up,
Oh,
just let me know and I can give you an extension. Good.
Thank you as well.
Cool.
Okay, I just had a quick question. I was reading the book earlier, and it says I had a question.
Oh yeah.
So
that's where these come
so
from.
it's like, Kate, is it just like?
Because the K would be like if I want to be within 2. Remember 2 was 75%. So if I put a 2 in there, it's 1 minus 1/4, which is 3/4, which is 75%.
Okay.
So that's the formula that gives me those percentages I gave you guys.
Last Monday was.
But it's not majorly important. We're not going to use it a lot. We're going to use Empirical Rule a lot more. But Chevy is important to know because it kind of is what Empirical is built off of. Yeah.
Okay.
Cool.
No, that's all. I was just confused.
I'll describe it.
One more.